All right, so welcome everybody this evening to our talk called Soils as a Stormwater Reservoir. So before we get started, I'd also like to take a moment to respectfully acknowledge that our work at EOS Eco-Energy is done on the traditional unceded lands and waters of the Mi'kmaq. And this evening's webinar is the second in our event series called How Nature Can Help Us Adapt to Climate Change. And soils are key to that for sure. I'll place the link to the event series in the chat box here in a few minutes in case you're interested in the rest of our lineup. We have events that are going on throughout the fall and winter this year. This event series has been organized in partnership with the Chignecto Climate Change Collaborative. And so if you're not familiar with them, they're a network of professionals working on climate change adaptation issues here in the Chignecto border region, so into Nova Scotia as well. And so now this evening's speaker is John Russell, and he's an agrologist and engineer. He works with the Agricultural Alliance of New Brunswick and has been facilitating their environmental farm plan in New Brunswick since 2004. He's been gardening for half a century, but since moving into newly developed residential areas, he's been mostly interested in improving the soil. And so before I turn things over to John, I'd like to ask everyone to remain muted if you can so that we can hear John clearly. And if you have any questions, we invite you to write them in the chat box, and then there'll be some different opportunities throughout the evening where I'll be able to relay your questions to John. If we have anybody listening on the phone though, we'll also open up things so that you can ask your questions as well. So thank you very much, John, and I will turn things over to you now.
Okay. Thank you, Amanda. I'll go right into the presentation and this up. Guess you can all see that. It's hard to know what the others see. Amanda asked me to speak about soils because I was talking to her about rainwater and different methods to catch it. And I was concerned that in generally our society doesn't pay enough attention to soil. And Amanda expressed herself that even though they work in soil a lot, the soil is sort of underneath where we're usually working and it's hidden from us. So there's a lot more we should know about it. We probably know less about the soil, maybe. I guess the soil, the oceans, and the space are some of our three unknowns, but we tend to think of the space as the unknown, but there's stuff right under our feet that we really sometimes don't know very much about. We're still learning about the biology of the soil that we sort of neglected for the last 80 years, I'd say. So we'll proceed here. Tonight, thanks for coming. I want to cover over sort of an overview of how I see the situation of catching rainwater and using the soil to catch the rainwater and the neglect of the soil in terms of using it as a stormwater reservoir in many cases. Talk about rainfall and some of the design criteria, the soil surface interface, or that surface of the soil that receives the rain. We're going to do in-depth on soil physical properties. So this is a sort of a starter session on some soil science aspects. Some you may be familiar with or you may not be. So if there are questions that come up there, by all means, put them in the chat or break in to ask. Then I'll talk specifically about soil water, so the water that's in the soil. And that's sort of broken out into different components, and how we fix the situation as I see it in terms of trying to keep some of that storm water in the soil instead of it just running off. And there are a lot of benefits. There can be benefits certainly for plant growth if we have a drought year, but there's certainly benefits in terms of reducing the stormwater runoff downstream. And we're getting into big infrastructure projects. Sometimes it's naturalized, it's not too bad, but it's still an infrastructure that often takes up some valuable land when we could be doing it on land that we already have available. First slide I want to show you is a rain barrel. And this has sort of got me thinking, well, I'm not sure if we really think enough about how we're catching rainwater, because this has been touted, and kudos to EOS for I think being one of the most prominent watershed groups promoting this. And I think it's great, but I don't think it's enough. So as you see, this one's overflowing. Then once that overflows, it probably goes into the rain garden. And this is an EOS project. I took this off your report, Amanda. And if there's really too much water, then some of these rain gardens will likely be overflowing, and you may have a stormwater retention basin at the bottom end to alleviate any concerns downstream from that. Sometimes we get the water sitting on the soil like this. This particular garden is basically on top of pavement with just a little bit of topsoil. There's insufficient soil health, and there's no infiltration down. So this certainly isn't good for the tomatoes. And once that water accumulates too high, I think it's already running off the end. And you know, it's sort of funny, they have a stormwater basin just downstream from this garden. It's not just to collect the rain runoff from the garden, but to me, there's no need of collecting runoff from the garden, because the garden should be absorbing that runoff. And you see sometimes you have ponding in the garden, and that's not good for the veggies. And here's another garden that was, the picture was taken on the same day, a few minutes before, but after 2 hours of heavy rains. And I don't see the water here. There might be a little bit water underneath this mulch, but even after the storm was finished, I didn't see any water there. So what's the difference there? I'm saying there are lots of loose open soil there, very good structure, and very good surface cover there that can intercept the rain and let it go down gently into the ground. And then this is the same time I took that picture from the garden that you couldn't even see the water, and from the about 10 residences uphill from me, you can see the water coming down. So there's obviously runoff from some of those properties, whether it was because their lawn was too compact, and I believe that's the case for the most part. They have slopes right down to the ditch for the runoff, which is great. It gets the water away from your house. But I see as later, it's great to get it 3 meters away, but I don't think we have to get it further than that away. The roof gutters are maybe going right into the back of their property. So they're trying to get that away because they're so scared of this water. I mean, you should be cognizant of the water, but you can't be too scared of it. And so they don't have very much water staying there, and they're probably watering their lawns in a dry season to try to keep them green. This is in a park that was built on top of a compacted subsoil. Probably just a skiff of topsoil put on there, and tried to plant some grass. And whenever I go there after a rain, even after a small rain, the water's just sitting on the surface of the ground. It's pretty flat, so there's maybe not that much runoff, but it's not absorbing into the soil. Trees fall down because they can't get their roots into the soil. The soil is too compact. There's no percolation. I'll talk later about runoff coefficients that engineers use when they're designing stormwater systems. And they say parts are usually 0.10 to 0.25, which means about 10% to 25% of the water runs off of parkland. But here, I'm sure it's much greater. If it rains a lot, then I think it'd be closer to 90% of that water is coming off. And whether that's calculated into the engineering designs downstream, I'm not sure. I'm sure no one's tested that soil. So we'll get into rainfall itself and what we're designing for. You see here, this is from the City of Moncton Sewer and Stormwater Design Manual. And they sort of plug this into a computer to figure out how high the peak flow is going to be at certain places down in their pipe system or their ditch or river systems. What this shows is called a Hyena Graph. It shows the rainfall over 2 hours. And this is the 1 in 100 year storm. So it's it's basically our biggest storm. And it's the numbers are what they use for Moncton for a 2 hour storm. So basically in 5-minute intervals, it starts raining a little bit. It rains about 20 millimeters in the first hour, and then you have a heavy rain shower for 5 minutes that drops down another 17 millimeters. And okay, I was putting my mouse on my other screen, so I guess you can see the 17 millimeters here, and then it sort of drops off again over there, but over the next hour, about another 20 millimeters of rain. So in total, that's 57 millimeters of rain that they say we have to take care of, because that's going to come off the land and overpower our stormwater systems. And with climate change, we're expecting that to happen more frequently, and those numbers are probably going to increase beyond what we see today. And besides that, we have more and more infrastructure as the years and the decades go along. So there's more that is at risk often when we have these big rainfalls. So now we're talking about the surface of the water and the soil. So when the water comes down, what happens to it? On roofs, what they use generally is 0.95. So 95% of the water is coming off, because I mean the roof gets wet a little bit, so some of that water stays in the shingles or on the steel siding roofing. But actually, when it starts raining really hard, a lot of these numbers approach 1. So basically, once the roof's wet, any extra rain is going to all come off, and they're going to have to deal with that. Again, the same thing with paving, like you little bumps in the pavement that hold some of the water when you have a light rain, but after the first few inches of rain, that's all going to go off. So for a 100-year storm, they calculate that as at 1. For lawns, the lawns should be absorbing that water. So it's anywhere from 5% to 35% are the design figures for lawns. Parks, I mentioned before, they use 10 to 25% generally. Woodland at low intensity, 2% of the rainfall they figure comes off. Again, it depends on the slope. You have to increase that for a high slope. But if you have a lot of hummocks and hills in that woodland, it'll catch a lot of the rain. The leaves at first will hold a lot of the rain on them for the first few millimeters. But then as we approach the design rainfalls, 100 millimeters per hour and 200 millimeters per hour intensity of rainfall, we're going to have 10 to 15% even coming off that woodland. That's sort of general numbers anyway. So with all that rain coming off, what's the volume that we have to come up, deal with? I mentioned for the 2-hour rainfall that they're using about 56 millimeters, which is 2 inches of rain. In 1999, within less than 40 hours, it was 163 millimeters that dropped at the weather station in Moncton, and there might have been some areas around Salisbury that got more than that. I think it was 127 in 24 hours. So just keep that in mind when you're thinking about the rain that's coming down. If you look at a sort of typical urban lot, about 20 meters by 30 meters, that's 100,000 liters. So 100 cubic meters of water. That's a lot of water to deal with. That's about 300 times the size of my rain barrel right now. And with these stormwater systems, normally you want to be able to hold the water back long enough that the peak flow in the brook or the stream or the river or even the stormwater system has gone through. And most pipes within the first couple hours after a heavy rain that it'll start to go down. But I mean, a lot of sort of medium-sized streams, it maybe takes 12 to 24 hours for them to get up to the peak. And rivers like St. John River takes a few days for the peak flow from upstream to come down and accumulate downstream. And I'll talk a little bit more about that in terms of plants, because we want to get that water out of the soil fairly quickly as well. I might as well pause here because this is our more technical part, if it's hasn't been technical enough for you. So I guess there are some things in the chat there, but no questions per se, I guess. Everyone can hear now?
Yeah, I don't have any questions yet, but yeah, and everybody can hear. We got Gail sorted out. I think you're good to continue.
Okay. So physical properties of soil, as you see listed here, that we talk about: texture, structure, moisture, aeration, and there's some other things that sort of go in with that. We'll go over soil texture in a minute. Soil organic matter is important in helping the physical properties of the soil. Also other biology in the soil, the soil biome we talk about a lot, and that influences the physical properties a lot. Drainage is an important one. Hydrologic soil group is related to the drainage. It's how easily water can go down through the soil profile. Porosity, that's related to aeration. So how many holes in the soil to let the air or the water in there. The soil structure they have there, and related to the soil structure is the aggregate stability. So it's how easily that structure stays stable, even with a heavy rain or traffic over top of the soil. So if you're an agrologist, you would have seen this this graph. This talks about the different types of soil. And if you're not an agrologist, you probably have heard about clay soil or sandy soil. This just breaks it out a little bit more. In New Brunswick, on the surface of the ground, we basically don't have any clay soils. In the Tantramar Marsh, you might be getting close, but it's more a silty, maybe silty, sandy clay. You might be getting close to that. But it's sort of peeves me off when people say they have a clay soil, because really it just means they have a poor soil that's compact. A clay soil can be a good soil if it's well managed, but a compact soil, whether it's clay or whether it's loam or whether it's sandy loam, to me is no good. And so people should say they have a poor soil instead of saying they have a clay soil. So these different categories are dependent on the categories of the three main soil particles. So the smallest soil size classification is clay, and that's made of like particular minerals too, like vermiculite is a type of clay mineral, and all these miculates. And those are sticky. So if you walk on a clay soil with your rubber boots, you're going to get the clay sticking to them, and your boots are getting bigger and bigger and heavier and heavier. And you'll find that often with loam soils. There's enough clay in it that you'll see that stickiness. So those are particles less than 2 micrometers. So I mean, they use sieves to sort these particles out in the lab to determine how much of each one is in the soil. Silt is silt. I mean, we talk about siltation in rivers and streams that covers over, you know, fish eggs and gravels and that. And silt is the very fine particles, and it's not as small as clay, but it has a soapy feel. and it disaggregates from the soil very easily, so it gets washed out very easily. It doesn't stick together like the clay does. So the clay is a little bit stronger because it sticks together. The silt will just get washed away. So that's often why we call it silt in the rivers, because that's the particle that gets washed down, and it's heavy enough that with a little bit of calm water, it will settle out. And then sand, sometimes they break this into fine sand and coarse sand. So the fine sand would be 20 to 200 micrometers, and the coarse sand would be 200 micrometers to 2 millimeters. So it's still, I think these are really tiny particles. Coarse sand would be what you'd find on the beach, like in Parley Beach. You know, that'd probably be 1-2 millimeters, maybe often. And the fine sand often gets deposited in the rivers along with the silt. It's the first particles to settle out, and then the silt would come after that. Clay, by the way, hardly ever settles out. Once it's in the water, it basically stays in the water unless you've got a pond that stays there for a few days, because it can take anywhere from days to centuries actually for that clay to come out of the soil. Yeah, come out of the water column, sorry. I think there are some interactions when it gets into salt water, so it's possible that once it reaches the salt water, it settles out, and then we get the tides of the Bay of Fundy that wash it around again. But like in well, I mean, the Dykeland soils and the Tantramar River, that's basically a lot of silt, because as I mentioned, it does detach itself fairly easily, so it moves around very easily in the river system. So that's why it tends to be more silty than clay. But there is a mix of those. I want to talk about density. And this is something that I think we should be measuring in a lot of soils, and we're just neglecting it. But this is directly related to compaction. So you should be able to measure the compaction of your soil by taking a sample, drawing it out, and weighing it, and seeing how much dry matter is in that volume of soil. It's important because for crop growth, if it's too compact, the roots aren't going to go into it. So you see over here, if you've got greater than 1.8 grams per cubic centimeter, that's the same as kilograms per cubic meter. And like water would be 1 gram per 1 gram per cubic centimeter, or 1 ton per meter. So it's related to the specific gravity too. It's the same as the specific gravity. So basically, we're saying this sinks because it's heavier than water. Water would be 1, the soil 1.8. 1.8, the soil is too compact. Pretty well all these except for clays. Well, clays never get up that high. Well, if they do, then it's really, really bad. But this is sort of useless if you're trying to grow something. And a lot of our soils, when they've got machinery run over it, like bulldozers and excavation equipment and things like that, that's what we're into. So that's what a lot of our subsoil is. And like in new development, we'll come and put topsoil on top of that, and the topsoil is nice and fluffy, and we see everything's fine. But the roots can only go down, like that garden I showed you, the water staying on top. The water and the roots just go down that far, and nothing goes beyond that. You might as well be on concrete. So you might get a few roots growing in the concrete, but not very many. So, and this is the reason why people fluff up their soils in gardens with rototillers and things like that, because you know the roots need soil that's fairly loose. It doesn't have to be really loose, but it can't be compact. So these are the densities. Sand tends to be heavier than the clays. The clays can have more structure, so it can be fluffier in a way if you have a good soil. And we'll talk about good soils in a second. I want to show you, if anyone's interested in testing your soil, There's a standard way to do this, and I'll maybe put the link in the chat there if I can get to my chat. Okay. You use a 3-inch core is a standard, and you cut this just about 2 inches long, and you decide where you want to take the core in your soil. So often you do it horizontally, so you'd have to dig a pit. So you dig down with a shovel or get an excavator, and you can pound this into the side, put like something steel on top, and a rubber hammer probably won't work. You're going to have a steel mass. Pound that in, and then you dig around it, you take it out. So this is about 2 inches long, and you shave off the ends here so that it's the soil's even at the end here and even at the end here, so you know exactly how much volume you have there. And then we could easily do this at home, put in the oven, dry that out. And on the dry soil, if you had a good weigh scale, a lot of labs around would have a good scale to weigh that and figure out what weight is in that standard core, and that could help you determine whether that soil is too compact or not. Another simple way of doing it is take a pen or a knife and just put it into the side. If you've got a vertical face, you can often sort of go different depths and see how easy it is to get that stick or that knife into the soil. And you can often tell by feel, okay, if that's a compact soil or if it's fairly loose. You're going to hit rocks, so make sure you're not sticking it into a rock. But if it's just soil there, it's a good way to know that. Sometimes there's certain layers where it's more compact than others. Like in agricultural fields, we often talk about a plow pan. So a plow pan is when you're plowing year after year with a moldboard plow, and it tends to put a down pressure right at the bottom of that plow. So if they're plowing at the same level every year, the same depth, then they'll often get a compacted layer of maybe just a few centimeters right at the bottom of that area that they're plowing down. So from here, I think I want to go into the soil reports. Yeah, we'll talk about this briefly, and then yeah, later on I'll show you some soil maps for regions of New Brunswick. Hydrologic soil group is how easily water can go down through the soil profiles. So the United States Soil Conservation Service, is called the Natural Resource Conservation Service now, classified soils back in the 60s, I think it was, into 4 different types according to how easily the water infiltrates down through. It's sort of related to drainage, but sometimes you can have a well-drained soil, like in eastern New Brunswick along the coast, Rishabukto, Bay de Vin area, Capillary, I think too. We've got a sandy soil on top, but underneath there's either sandstone that the water can't really go through, or there's compacted clay, not clay, but clay-ish material, probably clay loam. And so the water sometimes is fairly well drained because it goes down to that layer and then it goes out the side, but it doesn't go right down into the soil profile. So it's important to recognize that, because you may not have as much water holding capacity as you think, but it's maybe not too bad because it's filtering through the soil before it gets to a water course, rather than washing right over the surface and taking longer to get to water course. But most of our soils, like around Sackville, you've got a type of soil that is a deeper soil, but that's fairly heavy soil in the subsoil. And in Moncton, it's the case. It's even heavier, I think, in the subsoil in Moncton. And quite frankly, most of the province, we've got heavy subsoils. It's a finer material, like it tends to be a loam or clay loam or sandy clay loam, and it's often compact. The glaciers did a lot of good for our soil, but they were very detrimental at the same time. So they worked up this soil, and it's basically what gave us what we have to grow things in. But at the same time, we had about a kilometer of ice, they say, over top of the soil 40,000 years ago, and it compacted that soil so much that roots, they've been taking 10,000 years to try to get down there, and they haven't succeeded going much further than about 30 or 40 centimeters, if that. So the soils in the Sackville area that I mentioned, the Tantramar soil and most of what's in the marsh, it would probably be rated at D, a very slow hydrologic soil group. So very high runoff potential. So the water is going to go overland rather than down in the soil. Whereas if you go to some areas along the rivers, like along the Kennebecasis River, they have quite a few areas where it's sandy and gravelly right along the river. Along the St. John River, there are quite a few areas like that too. And when it rains, you don't see the water at all because it goes right down through. So it's really good in terms of not having runoff. It's not so good in terms of protection of groundwater, because if there's any contaminants in that water, it could go down into the groundwater, and if there are wells close by, they could be taken up in the wells. But we have very little of this. It tends to be right beside the rivers, and probably you're getting as much water from the river coming into that sort of gravelly, sandy layer as coming down from on top.
John, it's Kevin Deland here. Can I ask you a question? Or
yeah, go ahead, Kevin.
Well, you're talking about rivers, and I'm doing a lot of coastal engineering lately with projects. I'm on my 6th living shoreline plant restoration, virtual and physical. I was in Cocan with 6 mixed zones, and in Karakat and ocean surf last summer. And one of the things that, like with Helping Nature Heal, which are the group that are facilitating these workshops on behalf of the province and these communities, is that, you know, they're heavy into plants and soils, right? And certain plants are native to certain areas on river shorelines and to grow, and they call it stickiness. So I'm doing a coastline engineering project in PEI, and if you know how steep the cliffs are in PEI, and it's really hard in those steep slopes to grow anything. So this is my question, and a lot of people can't answer, because I took soil mechanics. I'm a civil engineer. I took many courses of soil mechanics. And one of the basic things in soil mechanics, which a lot of soil groups classifications don't explain, is called capillary action. Because these are written in the US, they don't get the cold freeze thaw like we do on the shorelines. And I read a study, because I'm actually creating a supervine, a sod blanket that goes out over a steep cliff with seeded plants, enough for those plants to take hold to slow down erosion. You're never going to stop it, but I'm basically making a supervine of diamond shaped onyx slope to prevent freeze thaw. And the reason why is that we're faced with a lot of capillary action. I just want to read you a statement from a paper. They were doing 3 tests on freeze thaw. Although it was observed that downward drainage exists, the majority of water migration is upward. Okay, upward, not downward. And I was taught in engineering, you can't push a rope and water always flows downhill, but it doesn't happen with coastlines, because when you've got capillary action of that water going to the cliff face, and that ice lens mixes with fine particles and winds, you get increased erosion, okay? But plants will slow it down. But I think a lot of scientists, or no, applied scientists, are missing the boat on capillary action. Anyway, it's just any comments on that?
Well, by capillary action, Kevin, you mean that like horizontal capillary flow
No,
or upwards?
both vertical and horizontal, because you're getting pull from the groundwater up, and then you're getting it from sideways to the cliff. And it's not what I'm getting at. Everybody thinks it's just runoff, but there's more
Okay.
to it. Is what I'm
I
getting.
could see that, yeah. So if the seawater comes up to a certain level, that's going to rise up into the, like either the
You got it.
groundwater or the ocean water. It's going to rise up. And so it's going to make those particles sort of saturated and loose, like several, well, I don't know, several feet maybe above the level of the water table.
Exactly, exactly. And I'll put in the chat a paper about it, because I think a lot of traditional groups are missing the boat on capillary action in our shorelines. And I think not enough science is done. I just put it in the chat. And I don't want to complicate things on soil mechanics, but capillary action is a big, it may not be a part for farming or growing in your garden, but in shorelines, it's a bit different, because you've got exposure all the time and PEI. And when you have exposure, freeze thaw, and then the wind hits it and freeze thaw, that soil gets, is like, it's either moved by wind, because you create ice lenses. You ever been along a cliff in the spring and you get all those ice lenses? Well, that's terrible for a cliff, and you can see the increased erosion. But I think capillary action is part of that too, because that water gets sucked to the side of the river or coastline and helps accelerate that upward motion of water hitting the cliff. Anyways, I don't want to diverse from, but I just want to let the reader know that, water always doesn't go downwards, is what I'm trying to get at.
I've always thought that on the coastline there, that the problem is the water going horizontally, because it's hitting a compact layer and following that along. Like it's what in agriculture, we call it side hill seepage in a field. Often you'll get water coming out the side of the hill and say,
Yes.
where's that water coming from?
You're correct. And sometimes you might have 3 aquifers in the same area. You got your
coming out at
seawater
3
and then
different
the
levels.
water table, and it even complicates things, right? So, but no one talks about capillary action, which I think is a missed issue. And I just put that link in there just for your own reading. It's a fairly recent study on the mechanisms of thawing, and that's the civil engineering geek in me. Sorry.
Thanks, Kevin.
Yeah.
I'm going to put a couple links there so everyone can, you can just click on those links in the chat and they'll come up in your browser, or you can try to save them. Oh, this is just a minute, I'll put, so I don't lose it. That I just put in a report, a link for the soil reports for New Brunswick. So it'll give you an idea of the type of soil in your area. It's a little bit hard to figure out which report might cover your area, but you'd have to search around. And I'm going to put the soil density. There's a nice fact sheet from the States on soil density testing.
That's another thing I don't see a lot, John, in constructions is a nuclear densitometer. What I used at Tech, I've never seen one in probably 20 years, actually tensioning the density of the gravel in construction.
That surprised me. I thought they would use something like that for road beds.
Yeah, never seen one in 20 years, and many inspectors.
Well, we don't do much for manure storages either. In Manitoba, they do compaction testing and all those layers, and we don't even know what a sheep's foot roller is in New Brunswick.
Yeah. We need more inspectors too. Now, sorry to ask another question, John, but I'm dealing a lot with Esri data from Geo New Brunswick, Bernie Connors, and they've done a world of information with LiDAR, surficial LiDAR.
Okay.
Is there any good layers of soil information now, like a LiDAR digital elevation model? Basically, you know what I mean? Like,
Yeah, no.
show depth perception with LiDAR accommodations.
They are working on that with one of the UNB professors, especially in regards to depth to water table and yeah, using that with LiDAR and to a certain extent the soil types. I'm not sure how much they're integrating that.
Okay.
But the soil maps that I gave you the link to are very general. Most of the areas in New Brunswick don't have good detailed soil maps, so they'll give you a general idea of maybe the soil in your area. But in a particular spot, it might be, it's fairly accurate, it seems, but it's fairly iffy. It covers a big area.
Yeah.
But what I'm using is just the stagnant maps, the PDFs basically. There are digital forms. They had problems initially that the transposition of that onto the New Brunswick maps, the projections were different. I think in New Brunswick they used the New Brunswick stereographic projection. These were using NAD 83 or something like that. So so there's a bit of a problem getting that digitally, but some people are using it digitally. I'm just not sure how exact it is, if it's an accurate transposition from those soil maps to the layers we're using.
Yeah, they're great maps. I'm just looking at them now. It's awesome.
Yeah, and a lot of people have never seen these. They've been on the web on the Agriculture Canada website for.
I've seen the geology maps a lot, but not the soil maps.
Yeah, and PEI has all their soil maps at 1 to 5,000 scale, from what I understand.
Wow.
So Prince Edward Island is much more detailed than Brunswick soil maps.
That's excellent.
While I was talking about soil texture, how much time do we have?
I got you off track, sorry.
No, but I sort of missed the point. Actually, LiDAR is one thing that I was going to mention, Kevin. When I was talking about the water contacting the soil, the flow paths are really important. So once that water starts to move, it's nice to know in what direction it's going and how much it's accumulating. And they have used LiDAR for that. We're not using it nearly enough, but you could map a whole area, like whether it's 1 acre or 500 acres or whatever, and figure out where that water is concentrating. And if you're going to build sort of deviations and all that, you can sort of cut those. If you want to slow the water down, cut those off. So anyway, there are tools out there using GIS and LiDAR and such that we should be getting good information for that. They have done that for the Blackbrook watershed, which is an experimental watershed in the Grand Falls area where they're potato farming. And they, about 10 years ago, they mapped all those little flow paths. So when they have terraces, deviation terraces, they can see exactly where that terrace is, where the water is going to flow and flow down into the waterway. I'm putting a link to a soil texture field test. When we're back there on the textures, one way to determine that is to put a little bit of soil in your hand. Put that camera there. And sort of break it up. I'm going to cover over my keyboard. And get some water and just spray the water onto that soil. Anyway, that video shows a lot better representation how you do that. And try to make a ball. If it's sufficiently wet, you should be able to make a ball. They say if you can't, then it means it's a sand. So on beach sand, you couldn't do this, but pretty well every soil you can make a ball. And then once you make a ball, I didn't put enough soil there. I should have about 5 times as much. you start pushing it up between your thumb and your finger, and you see if it's a clay soil, it'll go more than a couple of inches higher than your thumb or your finger. But this is by enough soil. This would probably go up about here. It's probably a loam soil, what I've got in my hand now. So that's an easy way to figure out the soil texture if you're interested in that, and see whether it's really a clay or not. And I think most times around here, you'll find probably it's a sandy loam.
That's easier than doing a sieve analysis, I tell you that.
But it's fairly expensive to do the sieve analysis, like about $60, I think, to do a textural sample. Okay, and density, hydrologic soil group. And now we're coming to those soil reports. So I've got a soil map here that I'll move over. This one's for the Sackville area, because I figure some of you are from the Sackville. So this is what Kevin was looking at online. You downloaded some of these, Kevin? Or, okay, you're on mute,
I did the northeast one near Miramichi just to see it's amazing, the detail.
Okay, so those forest maps.
Yeah.
Forest soils. So this, yeah, the different colors there show the different types of soil. Sometimes it's fairly similar, but you see these orange areas. I think you see my cursor going around there, do you? Yep, okay. So those are actually gravelly areas. It's a Gagetown soil, a sandy gravelly soil, and they say the surface, the SL is for sandy loam. So like some people that want to find gravel pits would look for these areas. But most of this is in the green, which would be a tormentine, the T, and there's a legend sort of lower down in this map, and the L is for loam. And then you get to the dikeland soil, and that's all Acadia. And the numbers, sometimes the numbers for the drainage here in the dikelands, the 1 is a well-drained dikeland, 3 is probably lower down and poorly drained, 4 is a poorly drained dikeland.
John, sorry to interrupt you again, but one of the things I didn't know till this year, that only 5% of the rock in the Brunswick is actually exposed. Like 95% has a soil layer. Is that correct?
I would imagine you'd be correct. Yeah, there are quite a few areas with limited soil, but yeah, I wouldn't say there'd be more than 5% exposed.
Yeah, I didn't know it was that high, that low for rock exposure. Okay. Yeah,
but pretty well all the coast, like all the southeast, like in they say this tormentine soil, and pretty well all the southeast here, we've got more than a meter of soil over top of bedrock.
Wow.
So
wow.
Some areas have less, like in Miramichi, like you're going to the Canadian Peninsula, and like some of the blueberry land only seems like a couple inches over top of the sandstone.
Yeah.
And so yeah, it's a different soil. But in the potato region, that's why, like in Carleton County, in Florenceville, Grand Falls area, this is one of the reasons why the potatoes grow well, because you do, well, most of the areas you do have enough depth of soil, although there is exposed rock in some of the potato fields around Florenceville.
Yeah.
So that's an example of a soil map. And then what we get from that is determine what type of soil. And these are specific information that I got. Actually, there's a description of that soil too. I had that somewhere, just a minute. This is in the one of the early reports. This was a report from the 1940s, and hasn't been redone. So this is the only report that actually covers only map that covers the Sackville area. It says the parent material is not particularly compact, which is good. So in Sackville, that tormentine soil, even though they say we've got it listed as very slow for the hydraulic soil group, the subsoil isn't as compact as a lot of the soils in New Brunswick. In Moncton area, it says Stony Brook. Often that is around here, and that is quite a compact subsoil. The roots have often been observed at a depth of 3 feet or more. Because it's not well drained, but it's more because it's not a very hilly land and the water goes down through it, and you have slow lateral drainage.
Well, you mentioned the roots there, John, and I know when I was teaching ecology, marram grass roots will go up to 3 meters deep. That's why they're
Okay.
really resilient in the coastlines for dune grasses.
Okay, so you can have a couple meters of soil move away, and your marram grass can still survive.
Yes, exactly.
It says the soils have high porosity, so that's good. Large amounts of precipitation can enter the soil, but it serves to raise the water table, because still that soil doesn't get too far too fast. So only by the drainage must be. So drainage is an issue, and it's more because it's sort of flatter soil, so the water doesn't get away, sort of going that lateral flow. But limited erosion normally. And then I'll bring up this other one. So they tested, did sample tests of these soils just to determine the qualities of it. And this one they said had 63% sand, this particular sample, so it should be fairly similar. There would be variation. The silt is 30% and clay's only 7%, so that's pretty low level of silt. And that, like gravel or rock, less than 10%, so that's easy to farm. That's why there's a lot of farmland in that area. So it's loose, it's friable. The bulk density 1.3, and you remember I had 1.8 there is the limit for most soils for the roots. So naturally, the surface of the soil is good for the roots. Total porosity is 47%, so that's what air or water could inhabit. But a lot of that water is sort of fixed to the soil particles and not even available for the plant roots. And what we're going to be looking at is macropores, and those are the big components of the spaces of the porosity in the soil, and that's what the water drains through. So this macropores is where we can store the storm water, and they say it's 12% in the upper layer of soil, and they're taking that 30 centimeters, they're saying, for this upper layer where they took the sample. And the hydraulic conductivity is pretty good, so the water does go down through there fairly well. You see 25 here. I'll go to the next slide, shows the soil underneath this 30 centimeters. So this is the subsoil, like from 30 centimeters down, a meter or 2 meters. They would have dug the pit probably about a meter deep. You can see it's a lot higher in clay. The other one I think was only 7% or 4%. A little bit more rock and gravel. The bulk density, that's right at that 1.8. So I often thought that the roots don't go down because of the water table there, and that could be the case, but it's also because the soil is too dense. So too dense for the roots, too dense for the water to go down. The roots don't like either dense soil nor saturated water laying there. So the roots aren't going to tend to go down through that soil unless you got cracks in it or something. So total porosity is only 30%, whereas the other one is close to 50%, and the macropores instead of 12% is only 5%. So in this more compact soil, there's a lot less water that can get in there and drain through it. And that 5%, that's a lot of the reason why there's poor drainage, because the water has, a third of the area, basically half to a third of the macropores to go through, whether it's vertical or whether it's horizontal. So that's going to stay around there. And as Kevin says, in a dry season, that's probably going to come back up through capillary rise, which
John,
is good.
John, sorry to interrupt, but is there a table that correlates shoreline like natural plants and the bulk density preferred of that root system?
I'm not a specialist in shoreline plants, so I couldn't
Yeah,
answer that.
or any
Kevin.
plant. Like I'm just wondering in the botany side, like I didn't know till a month ago, I was out with a botany group from the province that there's 15 types of willows.
Yeah. Okay.
So, you know, some willows might have better growth in certain densities of shoreline soils versus others. But I can't find any documentation on plant root systems and densities preferred. You know what I mean? Like correlating.
Yeah.
Because if you've got a shoreline, say in Grand Lake, and you want to plant willows, and you know the density, well, what type of willows? I can't find it. Anyways,
No, I don't know the specifics in willows. I think you'd find more variation between different species than just the different between the different varieties or the different species of willows. Like I think there'd be a lot more difference between an oak tree and a willow than between the willow species.
oh, definitely, yeah.
I think I'll just interrupt for 1 second, and I love all your questions, Kevin, and your energy. But I think, in the interest of time, we'll just.
Yeah, okay, I'll be quiet.
I was ahead of time at first, and now we're getting.
Thank you. Okay.
That's my engineering of me. Sorry.
The PEI lab has a soil health test now, and it's expensive. It's about $100. But besides, they're giving you the texture, but they're also giving you things like the soil respiration, which is an indication of the life in the soil, the biology. And what's really interesting, and we haven't started using that number very much, but is the aggregate stability. So that tells you a little bit about the structure of the soil. And I'm going to take my, I'm going to stop the share so that you can actually see what I'm doing. I see there's something else in the chat. I got some examples of soil, and I want to show you the difference. So when we talk about aggregates, we talk about the soil sticking together. Those particles that I showed you, very fine particles, but they stick together in bigger clumps. And when you have a nice garden soil, you've got root stock going through there, of course, but it's very loose. It's falling apart here. And you see these little things. These are PEDs. These are soil PEDs. These are what we call aggregates, and we want them to stay like that. We don't want you to crush them up like a rototiller might do, or like someone walking over by foot or with a tractor would just crush those up. So they have to be stable enough that they're going to resist, say, foot pressure over top, but loose enough so that they break up. So that's an example of some garden soil on the surface, and then you dig down into the subsoil, and this is the sort of thing that you get. So I encourage you folks to look at your soil, to dig down and see when you get into that. Like if this was dried out, it would probably just be like a rock. I wouldn't be able to break it up, because some of this I was using a pickaxe, and I had to use the sharp edge of the axe because of the pick, because nothing else would go through it. So when you see it smeared like this, it means that, yeah, there's no structure to that at all. It's just one mass of compacted dirt. We shouldn't even call it soil, I guess. I've got there's some other soil here again. Where is this from? Yeah, this is from a construction site where we're trying to make a garden. And again, it's just a mass of soil. There are no roots, first of all. There's no organic matter in it because it's probably subsoil, but it was just all compacted together. The machinery would have gone over it. And I can break it apart, but you don't see it. You don't see it crumbling apart like this soil would have. I mean, this is a lot nicer color too, but because it's got organic matter in it. But look at the difference in that. And like, you won't get roots going through this. We've got to loosen this up to get roots going down into it. And then even at the extreme, this rock is actually sandy loam or loamy sand soil. And this was put in my front yard by the city contractor. And it's dried out, of course, but it's as heavy as anything, as dense as anything. And this is what people, I say, would call clay. It's not clay at all. It's closer to a sand than a clay. And it's just compacted. There's no life in it. There's no roots in it. It just doesn't crumble up at all. So this is some of the stuff we have that's underneath. Sometimes we put topsoil on top of it, so it looks like stuff is growing, but it's not growing nearly as well as it should. And there's no water going to go down through that. Clean this up a bit. Okay, so I'll go back to the screen share. And okay. So the soil health report, I'll go to the next slide. I'll go to the next slide. Okay, and this is an example of what I just showed you. So it's in French for those that understand this, but it says this is increasing compaction along this line, and this is increasing what they call restructuration. So they're getting structure back to the soil. So here the aggregates are separated here, not too much, but you can break it apart with your hand. Here you've got big clumps, and here it's just one big mass. And here's an example of the surface of the soil. There's no infiltration. You can sort of see it's puddled there, like it's like on the bottom of the puddle. That's where your clays would settle, and then when it dries out, it cracks. So you know you've got no structure there. There's no organic matter. Very dense, no porosity. There's no place for the water to go. Even after a wet spring, you dig that up and the soil's dry underneath because the water wasn't able to get off. And when you get a rainfall, the water just washes right over there, just like it would off an asphalt or metal roof or off concrete or pavement. Okay, so now we're getting into an important point, so I'll try to get through this. The soil water content of the soil is important to understand. We're breaking it into 3 different categories. When you've got saturated soil, you can't put any more water in there. The first part is the part that drains. That the plants really don't like this because it takes up space from the air. When you've got saturated soil, there's no air, and the roots need the air. So you go down here, and this is where we want to be. It's the area we call available water for the plants. Field capacity when the soil is nice and moist, and permanent wilting point is when it's dry and that plant is at the point of not being able to get any more water. So it can be pretty dry before it gets to that permanent wilting point, but usually the plant starts to suffer a little bit before it gets there. This is another representation of how that works that's a little bit more visible. So the gravitational water, that's in the macro pores that we talked about, that 12% or 5% in the subsoil. And that's if you can get drainage down, that what drains down, or if you got impermeable subsoil there, it'll probably just drain laterally. Then well, they call this capillary water, so it's what's attached to the micropores, and this is what, as Kevin said, can come up from below, and just by that sort of magnetic force, that attractive force, it can rise actually in the soil. And this is the water that's a little bit tightly held, but not that much, so the roots can get at this water. And then this hygroscopic water, the roots can't get this at all. It's too tightly held to the soil particles. And this shows how much water you have in the different soils. So in the sand, you don't have as much of that tightly held water, and you do have more of this brown, this excessive gravitational water. And this is sort of interesting. So it means in the sandy soil, we can actually store more water than we could in a typical loam or clay soil, because they're more of those macropores. Although if you look at it, there's less total water in that soil. Antecedent moisture is important to be cognizant of when you're talking about the soil accepting water. If it's rained 2 days before and that soil hasn't drained out, then it can't accept the water like it should. So in some areas, I don't know, maybe style drainage we're thinking about to try to get that water away. We'd like to drain it out in 12 to 48 hours, because otherwise it can hinder plant growth. But as I say later, it's nice to try to keep it that long so that you reduce the water flow in the streams, whatever's at risk in your area. So if we want to calculate the potential storage capacity, if we have 12% in that typical tormentine soil, we could store in that first 30 centimeters, theoretically, we can store 36 millimeters of rain there. So it rains 36 millimeters, and that's in that top layer of soil, and then it starts moving down into the subsoil below. If it keeps raining, we can that 35 millimeters should be able to go into the soil below if it's been drained out. The gravitational water has gone out, and then we can get another 36 up above for a total of 71. But the deeper we go with that high porosity soil, the more water we can store. So instead of 30 centimeters, if we can get that loose soil down 40 centimeters, we can put more water in there. We can reduce the runoff, increase the stormwater storage, and we can have more water storage for dry periods of the year as well. And those roots could go down and get that, or you got the capillary rise sort of coming up through that. So this is what I've talked about, the macropores. If the soil is dry, like if it's really dried out, down close to that wilting point, we can also store some of this water. So it takes a little bit more to get through the soil profile, but there's potential. If it's a dry soil, then we can fill this up, and then we can put the gravitational water in there. So that's often what we want to do by catching little rainfalls, is to just replenish that available water in the soil. So I want to go over some slides how I think we should be working with the soil, from especially in municipal areas, what I'm considering here. But if there are any questions right away, I'm gonna, oh no, I think I'll show that video. Yeah, I guess I got all the links there that I wanted to. So tormentine soil, man, it's that the names they give to soils, they're what soil scientists use to differentiate one soil from the other. And often what they've used is basically the name of the community where they first found that soil. So if they dug a pit out in Cape Tormentine, they say, oh, we haven't seen this soil before, let's call it a tormentine soil. So it's simply that. And then everywhere else they found that soil, that's the name that they use. So compacted soils is what I'm concerned about most. So like that soil that I showed you, we've got to loosen that up if we want roots going down there and have water infiltrating, have plants growing like they should be growing. We can do that in different ways. A deep ripper, maybe down 4 feet, a subsoiler, the agricultural operations sometimes use those. It's a little bit tough because the soil has to be dry for it to work. You want to fracture the soil. So in this case, there wasn't any water going down in it, so it does fracture nicely. I think more contractors should have sort of digger tooths or those subsoilers sort of attached to whether it's their bulldozer or excavators or backhoes, and that's what we used. And this is a digging tine. So for a garden, if you want to go deeper, like it's a little bit like the double digging. It's maybe more common than it is now. Now we tend to try to keep the layers on the same level, but we try to go down with something like a digging fork or broad fork. Broad fork maybe goes more than 15 centimeters, but probably not more than 20 centimeters, 8 inches. So this is an example of just a 60 centimeter, 2 foot long tooth on a backhoe that worked really nicely in loosening up that soil. And I think they should do that for all construction sites before they put down any subsoil. We've got some concrete slabs we're taking out too there. And what tool is best really depends on the soil conditions. So this broad fork, it has 2, 4, 6, 7 teeth on it. If you got a compact soil, you're not going to be able to get that down there. You got to weigh 300 or 400 pounds in order to push it down, I think. But for most gardens, this is sort of nice to just keep the soil in good shape. They say once you're really doing well with your soil, you shouldn't need this at all. Kevin was talking about roots that go in what 3 feet, 3 meters on the marram grass. And if you look at this scale, that's actually down 6 meters with the alfalfa. And it's incredible to think of that. Like I can see in sand dunes and shorelines, you can get that depth. But with our compacted soil, in the prairies where they got nice loose grassland soil, they probably can get that depth. In a gravel soil beside a river, I know someone in northern New Brunswick with a field along the river had their roots down 26 feet deep. They had a pit dug beside their field. But it'd be really nice to get the roots down that deep. So it promotes soil aggregation, improves the soil health, and more we're especially with the soil improvement mixes like green manures, we're putting a variety of crops in there. So some roots will be fibrous and on the surface, and others are a deep tap root to try to break up the soil. This is an example of a trap root here. This is a daikon radish that is about 43 centimeters long, I think, about 17 inches long. And that was all under the ground too. Sometimes you'll see some of it sticking out. So that's an example of a tap root, and it's a crop that's being used a little bit more, just an annual crop. And we really shouldn't have taken this out of the soil. What you want to do is for it to stay in the soil and then rot, and then you basically have that hole going down in the soil. So it encourages the biological life to go deeper. The air is going to go deeper. It's like putting an aerator, like people do in their lawns, an aerator. These are little aerators that are going 15 inches deep. And then another thing we should be doing is make sure we have cover on the soil. So that garden I showed you with the puddles on top, I don't like that because I don't think we should have bare soil. When the rainfall is actually going to start to destroy the structure of that soil. The soil cover keeps the soils alive because the biological life it doesn't like to be sunburned and dried out. It likes to be moist, and it'll help create those aggregates in the soil. It aids in infiltration because the water goes slowly down instead of just hitting it. And when the raindrop hits the bare soil, it tends to seal it off. So it decreases the infiltration. Or if leaf matter or grass or something on top, then it'll allow it down. Yeah, in sandy soils, it wouldn't be an issue, but in soils with some clay and silt, that's an issue. The soil absorbs the runoff and slows the movement of water, and as I mentioned, reduces the raindrop impact. So there's less erosion too, because you don't break up that structure right at the top. And the representation on the right is if you go into a field, you can sort of use this for a visual to figure out how much cover there is in the field. We do this in agricultural fields. We try to get 30% cover is the ideal, and in no-till systems, that's what they're looking at. When you're plowing up, you're normally getting less than 10% residue on the surface, which makes the soil more susceptible to erosion and to destruction of that soil structure. Most of the soils we're plowing in this area are forage soils, so there's lots of roots in it. They've been in grasses or clovers for maybe 5 years or more, so they usually got good organic matter, manure add and things like that. So but the more cover you get on the soil, the better it's going to be in a lot of respects. The people that clean their gardens in the fall, I don't agree with that at all. I think everything should stay on the soil as long as there are no disease issues. Leave everything as a cover on that soil, and the earthworms will love you. The earthworms need something on the surface to take down deep. That's their food. So if we clear the surface of the soil, we're depriving the earthworms of all their food. An example of a wooded area where the water all gets absorbed. Again, this was the same day that I took all those other photos with the ponding in the park and in the gardens. And of course, you've got a good structure of soil here. It hasn't been tramped over. You got some trees sort of letting the water down easy on the ground, and not great cover on the soil, but you've got quite a bit of debris there that slows things down and probably keeps the earthworms likely working underneath. Earthworms some areas are considered invasive species now, so just be cognizant of that, because some forests, they're actually eating too much of the leaf litter and leaving things bare. And then I wanted to show you sort of the way we're using our land in terms of the slopes. This is an example of a potato field cultivated up and down. This is one where they turned the rows around and cultivated across the slope, and then they put a grass waterway down here to let the water out. So we call them terraces, or the diversion terraces or diversion berms. They slow the water down. It'll still run off, but run off a lot slower than if that potato row was up and down the hill. So we've got to be cognizant of that when we're doing any type of natural infrastructure. Slow that water down so it can absorb into the soil. And this is a diagram of those two fields, and then I'll show you some data from them. So this is the runoff when the potatoes were up and down in the row. This is an example of, I think this was a whole season. We had 180 millimeters of rain. Of rain that came off that field actually after it rained. And with the diversion waterways, there was only 25 millimeters that came off. So you can see the big reduction. So all this water here, that stayed in the soil. And that stayed in the soil to grow the potato crop. So in some cases, it might make it too wet, but in this case, I think it really improved the crop. And it reduced the runoff into the stream below. And when you've got like ryegrass underseeded under the barley, it's a little bit more grass. So even if it's up and down, it's not that bad. But in our lawns that have compacted subsoils, we're not getting the infiltration. This is a nice loose agricultural soil. I think in a lot of our lawns, it'd be more like this for a compacted subsoil, and more like this for a nice loose soil underneath. And here's the water running off. So we had some, this is the Hyena Graph, or the rainfall. So after 40 minutes, it rained really hard after the start of the rain, and it rained again about 100 meters later, 100 minutes later. And then this is the hydrograph, or the discharge of the water in the ditch or the stream, or the flow coming off that field. So in the yellow, that's the one that was cultivated up and down, water comes right off. The one that was cultivated across the slope, the water stayed among those potato rows, and it wasn't until we got a little bit more rain then it sort of maxed out, and then it started flowing off. So the slopes and the berms, like if we have any opportunity for ponding, if it's not going to create any detrimental impacts, just stays for a few hours, by all means. This is an example of a tree root actually created a ponding area here. That often happens in the soil. A tree falls over, it stops the water from going, the water ponds there, and that's why we're getting a lot less water coming off most of the forest land traditionally. So they were using 2% of the water going off. Swales and berms to go across the slope so the water's not rushing right down the slope. Wasp cobs, they used a lot in some of the flatter soils, say in the fields in Ontario, water and sediment control basin. That's basically a berm with a drainage pipe. So it lets the water down slowly through the drainage pipe, and it's designed maybe after 2 days, it'll have all the water evacuated after a big storm. But all that water will stay there. They won't have any erosion because the water's not rushing across the field. So they do this maybe every 10 or 15 acres, something like that. They'd have an area with a berm at the bottom and an inlet. And as I mentioned, get the water away from the house, but after 3 meters, I don't think is an issue. So try to get that absorbing in after 2 or 3 meters. And I wanted to point out that I think it's important for you to recognize where you are in the watershed when you're thinking about stormwater control. So higher up in the watershed, you want to keep that water back as long as you can and let it off gradually. So let the water get down through the stream, and then you keep that peak flow lower. Keeps the stream flow more constant too, because you'll have water coming in a little bit after the fact and keeping some water in the stream. But then if you're down at the bottom of the watershed, it might be detrimental actually to keep that water. It might be better to actually store it than to slow it down. So slowing it down, like I'm thinking maybe roof water. There might be some areas where you want the roof water to go right off right away and not hold it back. Because if you hold it back for 15, 20 minutes, and then it goes to the stream, you're going to get all the water coming from all those other areas at the same time, and you might actually be increasing the peak. So it's something we should be considering a little bit. And yeah, one thing I'd like to say about like rainwater collection systems, barrels. We should be emptying those before rainfall if we want to control a little bit of the stormwater runoff. So they'll catch a little bit of water, which is great. So they'll reduce the flow going off. But if the rain barrel is full when it rains, it's not doing anything in that respect. Sure, if it gets dry, we'll have water, but it's a little bit of management there. And so in summary, I'd say know your soil. Go for a walk in the rain when it's so you see where the water's flowing and whether it's infiltrating into the ground or whether it's running off. Decompact your soil and keep it decompacted with good soil life and good soil management. You can keep it decompacted and don't run over it. Cover the surface to improve the infiltration. Slow down the water by using those berms, or vegetation also will slow that water down. And have an idea how much water you can store. If we're really looking at those major storms doing the damage, it's those major storms that we've got to be cognizant of and try to manage for those severe runoff conditions. And that is tough. And the soil can only take so much, but I think the more we put in the soil in all our rainfalls, it's going to be beneficial. And that's all I wanted to go over. And we have 5 minutes.